Hi, hello, welcome you all for the second class of your fluid mechanics subject. So today, in the previous classes, we discussed about some properties of the fluid and what is the fluid and what is the fluid mechanics and some basic terms which we are used in this fluid mechanics subject. But in today classes, we are going to start the new topic, that is classification of the fluids. Okay, so here in this we are going to classify the fluids as follows. Here we can see the graph here, that is shear stress versus the velocity gradient. So in this graph only we are going to classify the fluids. Okay, so this shear stress, it represents the ideal solid and ideal fluid. Okay, if it is having the velocity gradient, then it is an ideal fluid. If it is having the, it is not having, or the velocity gradient is equal to 0, then it is the ideal solid fluid. Okay, and this line is representing the ideal plastic fluid. Okay, and this curve is representing the non-Newtonian fluid, and this linear line representing the Newtonian fluid. Okay, so these are some classifications on the fluids. Okay, next one is here we can see is the classification of fluids here: ideal fluid, real fluid, Newtonian fluid, and non-Newtonian fluid, ideal plastic fluid. So these fives are the classification of the fluids. Okay, what are those? Ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. Okay, so next we go through one by one. What is the ideal fluid here? A fluid which is incompressible and it's having no viscosity. A fluid which is incompressible, we cannot compress that fluid. It is incompressible and it is having no viscosity. It does not have any viscosity. Viscosity is the property of the fluid. The fluid which is not having the viscosity properties, then it is called as a ideal fluid. Along with this, no viscosity, it should not be a, it should be a incompressible. That means the fluid should not be compressed. We are not able to compress that fluid. That is what incompressible, okay, is known as a ideal fluid. But it is an imaginary fluid. What is this imaginary fluid? Is nothing but the ideal fluid is one of the imaginary fluid. Means whatever the fluid existing in this universe, all the are the compressible one. All are the compressible one, and all the fluid will have viscosity. All the fluid will have the viscosity. That's why this whatever this fluid is there, that is ideal fluid is there, that is the imaginary fluid. Okay, all the fluid which exist have some viscosity. Okay, all the fluid which exist in our universe will have some viscosity. If the viscosity is zero, so such type of fluid is called as a ideal fluid. But in our universe, all the fluid which have exist in universe will have some viscosity. That's why this ideal fluid is the imaginary fluid. It is one type of imaginary fluid. We can imagine that fluid, but in actual universe we do, such type of fluid will not exist in our universe. Okay, so next one is real fluid. A fluid which possesses the viscosity is known as the real fluid. All the fluids are a real fluid which exist in our universe. Okay, so which possesses viscosity means which have the fluid which have the viscosity, then such type of fluids are called as a real fluid. The fluid which does not have the viscosity, such type of fluid will have will called ideal fluid. Okay, but in our universe, see here, all the fluids are the real fluids. All the fluids are the real fluids. This ideal fluid is the one imaginary fluid, and the real fluid is which possesses the viscosity, means which is having some viscosity. The fluid will have some viscosity. Viscosity is nothing but what? It is a property of the fluid which offer resistance to the flow of fluid. Okay, so all the fluids in the universe will have some viscosity. That's why those type of fluids are called as a real fluid. Okay, next one is the Newtonian fluid. It is the real fluid First we can define this Newtonian fluid by using whether it is the real fluid or ideal fluid. It is the real fluid in which shear stress is directly proportional to the rate of shear strain. It is a one real type of fluid, means this type of fluid will exist in our universe. A real fluid in which the shear stress is directly proportional to the shear strain is known as a Newtonian fluid. Okay, Newtonian fluid. If shear stress is directly proportional to the shear strain, then such type of fluid is called as a Newtonian fluid. It is a real fluid. Okay. Next type is non-Newtonian fluid. See here, non-Newtonian fluid. A real fluid in which it is also a real fluid in which shear stress is not proportional to the rate of shear strain. If these two are proportional to each other, then it is a Newtonian fluid. If these two is nothing but shear stress is not proportional to the rate of shear strain, then it is called as a non-Newtonian fluid. Non-Newtonian fluid. Okay. Okay. How to define the Newtonian fluid? If it is the real type of fluid, if the shear stress is directly proportional to the shear strain, then it is called as a Newtonian fluid. It is and non-Newtonian fluid. It is also a real fluid in which the shear stress is not proportional to the rate of shear strain. Is known as non-Newtonian fluid. Okay. Next type is ideal plastic fluid. Ideal plastic fluid. A fluid in which shear stress is more than the yield value and shear stress is proportional to the rate of shear strain is known as ideal plastic fluid. So we know the ideal fluid. Here it is the ideal plastic fluid. So in the it is defined as the fluid in which shear stress is more than the yield value, more than the yield value, and shear stress is proportional to the rate of shear strain is known as ideal plastic fluid. Its shear stress value is more than the yield value of that fluid, and shear stress is proportional to the rate of shear strain. If these two conditions obeys, then it is called as the ideal plastic fluid. What are the two conditions here? Shear stress is more than its yield value and the shear stress is also proportional to the rate of shear strain. Then such type of fluid is called as the ideal plastic fluid. Okay, so these are the five main classification of the fluids. Next we will move on to the thermodynamic properties. Okay, in the yesterday class we discussed about the fluid properties, and now we are going to start the thermodynamic properties. Okay, so what is this? Fluids consist of the liquids or gases. As you know, how to define the fluid? It consist of both of liquid and gases. Fluid is nothing but what? It includes both liquids or gases. Okay, gases are compressible fluids. Yes, the gases are called as a compressible fluids because we can easily compress the gases. We can easily compress the gases than the liquids. Okay, than the liquid. That's why the gases are compressible fluids. Okay, the change of pressure and the temperature, the gases undergoes a large variation in density. So due to the compressible fluids, its pressure and temperature is going to be changed. After compressing the fluid, its pressure and temperature is going to be varies. Okay, the gases undergoes the large variation in its density. Due to the change of this pressure and temperature, its density, which density? Gases density is getting varies. That in large quantities. Okay, so we know that universal gas constant gas equations, PV is equal to mRT. PV is equal to mRT. So you can PV is equal to RT. If it is, you can take that mass is equal to 1 kg. Okay, P by rho, that is equal to volume is nothing but what? Mass per density, or P by rho is equal to RT, where P is equal to absolute pressure of the gas in Newton per meter square, where P is nothing but what? Absolute pressure of the gas in Newton per meter square. This V is equal to specific volume, that is given by 1 by rho, that V. This V is representing the specific volume, that is equal to 1 by rho. That's why this P divided by rho. V is nothing but a specific volume that is given by 1 by rho. That's why it is P by rho, which is equal to RT. Okay, and this R is equal to gas constant. This R is equal to gas constant, and the T is equal to absolute temperature in 0 degree Kelvin. Absolute temperature in 0 degree Kelvin. Okay, so in the thermodynamics properties, fluid consists of liquids and gases, but the gases are compressible fluids. Okay, so after compressing the fluids, that gases pressure and temperature changes, and also its density varies in large quantities. Okay, these are the uh, PV is equal to MRT, that is a gas constant equations. Okay, next, dimensions of gas constant, that is R. In the MKS system, R is equal to P by rho T, kg of meter per kg degree Kelvin, kg degree Kelvin. This is MKS system. In the SI system, joule per kg Kelvin, joule per kg Kelvin, 287 joule per kg Kelvin, like this. Okay, 287 joule per kg Kelvin, that is the dimensions of gas constant. Okay, joule per kg Kelvin. Next, isothermal and adiabatic process. In the thermodynamic properties, we have to uh, know about these two, isothermal and adiabatic process. Okay, so what is this? If change in density occurs at constant temperature, change in density occurs at constant temperature, then the process is called as a isothermal. Isothermal, iso, same, thermal is temperature. That's why if its temperature is remains constant, is called as a isothermal processes. Okay, so if change in density occurs at constant pressure is nothing but for isothermal processes. Okay, then the process is called as a isothermal, and the relation between the pressure and density is given by P by rho is equal to constant. P by rho is equal to constant. This is the isothermal processes. This is the isothermal processes. Remember these equations. P by rho is equal to constant. Okay, what is the isothermal? Isothermal is nothing but what? Constant pressure. During the constant pressure, if the change in density occurs, then this process is called as isothermal. Okay, so in the relation between the pressure and density is given by P by rho is equal to constant. Remember these equations. Okay, next one is adiabatic process. Adiabatic process. If change in density occurs with no heat exchange to and from the gas. Okay, already we know that the adiabatic process is nothing but what? If change in density, if change in density occurs with no heat exchange, to and from the gases. There is no heat exchange takes place between the gases and the system. Between the gases and the system, and in that cases, if the density change in density occurs, then the process is called as a adiabatic process. So at constant pressure density change occurs, then it is called as a isothermal process. At if there is no heat exchange to and from the gases, then also the density changes, then it is called as a adiabatic process. Okay, uh, these two are the differences. Density changes when constant pressure is called as isothermal. Here also density changes when there is no heat exchange between the gases and the system. Then the process is called as a adiabatic, and the relation between the pressure and density is P by rho raised to K is equal to constant. P by rho raised to K is equal to constant. Remember these two equations. This is for the isothermal process and this is for the adiabatic process. Okay, isothermal process is nothing but what? At constant pressure density change occurs, and the adiabatic process is nothing but what? Heat exchange. There is no heat exchange takes place, and the density changes, and that time density changes, then it is called as a adiabatic process, where K is the ratio of specific heat of a gas at constant pressure to the constant volume. That is, this K is nothing but what? Cp by Cp by Cv. Cp by Cv. This is what? Constant pressure, that is Cp, divided by the constant volume, that is Cv. K is equal to the specific ratio of specific heat of the gas at constant pressure and the constant volume, that is K is equal to Cp by Cv. Cp by Cv. So okay, these two are the processes. Okay, adiabatic and isothermal, you should know about these two things. Okay, next properties, thermodynamic properties of the fluid is surface tension. Surface tension, see here, we can take the three particles here, particle A, particle B and particle C here. Okay, this particle A is completely immersed in the water, completely immersed in the water, that is nothing but it is surrounded by the liquids, it is surrounded by the liquids only. And so here you can take the particle B, it is also surrounded by, maximum portion of this particle B is surrounded by the liquid only. The maximum portion of the particle B is surrounded by the liquid only. And you can take the particle C here, water particle C here, 50% is surrounded by, its 50% is surrounded by the liquids and the 50% is surrounded by the air or the gases, air or the gases. Okay, so here by using this particle C, we can define this surface tension. We can define this surface tension, and we should know where the surface tension properties exist. Where the surface tension properties exist. Okay, here if it is surrounded by the liquids, this particle A is surrounded by the liquid, then the force existing surrounded on this particle is same. All the tensile force existing on the surrounded particle A is the same. It is having the equal forces in all the directions. Equal pressure forces are the forces in all the directions. Here also it is having the more forces or the pressure towards the downward side, and also it is having the maximum, it is having the same pressure or the forces in all the direction. But in these cases it does not happen like that. Okay, it is having the more forces or less forces or uneven forces in the all the directions, due to only the 50% of the portion is surrounded by the liquid, and the another 50% is surrounded by the gases or the air. Okay, so by using this particle C, you can define it. Here it is defined as the tensile force acting on the surface of the liquid. Surface of the liquid, the tensile force is acting on the surface of the liquid in contact with gas or on the surface between the two immiscible liquids. Okay, the surface tension forces, tensile forces acting on the surfaces, okay, of a liquid in contact with the gas. This is surrounded by the gas, this is gas and this is liquid. Contact with the gas or on the surface between the two immiscible liquids. Two immiscible liquids is nothing but one liquid is liquid here, another liquid is gases. So these two are called as the immiscible liquids. One is, this is the liquid and this is the gas here. So these two fluids are called as a immiscible liquids, such that the contact surface behaves like a membrane under tension. Membrane under tension, that means, so these surfaces, whatever the surface is there, this is act as the membranes. This is act as the membranes because this surface is subjected to the two types of fluids. One is liquid, here it is, this surface is acting, means it is subjected to the liquid as well as the gaseous, as well as the liquid gaseous. So whatever the particle which are present in this surface is called is subjected to the surface tension. It is subjected to the surface tension. Why it is so? It is in between the two immiscible liquids, in immiscible liquids, that is, one is liquid, another one is gases. That's why the particle which are present on this surface is subjected to the surface tension. Okay, so and this surface is act as the membrane under the tension, because the surface is having to having the contact between the gases and liquids. So it is acted like a membrane. So whatever the particle which are present on this surface is called as, it is subjected to the surface tension. Okay, and it is denoted by the Greek letter rho, sorry, Greek letter sigma. It is denoted by the Greek letter sigma. This surface tension is denoted by the Greek letter sigma, and its SI unit is Newton per meter. Surface tension unit is Newton per meter. Okay, this is the surface tension. Next one is surface tension on liquid droplet. Surface tension on liquid droplet. How the surface tension is acting on liquid droplet. Okay, so here surface tension on a liquid droplet. So this droplet is cut into two halves. So there is one droplet is there, liquid droplet is there, that is cut into two portions, and this is one portion and this is a another portions. Okay, so first it is subjected to two forces, one is the tensile force, another one is the pressure forces. Okay, so first one is, this is the surface tension, it is subjected to the tensile forces or surface tension force. So tensile force due to the surface tension acting around the circumference of the cut portion. So this is acting. So this is denoted by the sigma. So this, it indicates it is subjected to the surface tension or tensile forces. Okay, which is given by sigma into circumferences. Sigma into circumferences, because at circumferences only the tensile forces is acting. So that's why sigma into circumferences, that is sigma into circumference of this droplet is given by the phi d. Circumference is given by phi d, that's why sigma into phi d, it is equation number 1. Okay, and second one is the pressure forces on the area, pi d square by 4. So this is here. You can take the another half of the liquid droplet. So it is subjected to the pressure forces. Okay, pressure forces on that area, pi d square by 4. This area of this is pi d square by 4. Now we can get the pressure force P into pi d square by 4. This is equation number 2. We can equating 1 and 2. By equating 1 and 2, we will get that P is equal to 4 sigma by d. 4 sigma by d. So this d, 1 d, and here it is d get cancelled. Okay, and this phi and this phi is get cancelled. So we know that p, we get the p is equal to 4 sigma by d. By equating equation number 1 and 2, we will get the P is equal to 4 sigma by d. This is the surface tension on the liquid droplet. Okay. Next, surface tension on a hollow bubble. That is that is for the liquid droplet, and this is for hollow bubble. A hollow bubble like a soap bubble. So already we know the soap bubble, how it is having the shape. Okay, how it is having the soap bubble. So it will flow on the air only. Okay, the hollow bubble like a soap bubble in air has two surfaces. In air has a two surfaces in contact with the air. Okay, thus two surfaces are subjected to the surface tension, because if you are having one soap bubble, it is subjected to the two surfaces. One is outer the surface of the soap bubble and inside the surface of the soap bubble. It is subjected to, in both the sides it is subjected to the air. It is subjected to the air. Inside that hollow bubble we are having the air, and outside that bubble is also subjected to the air. That's why we can say that air has the two surfaces. Bubble in air has two surfaces in contact with the air. Okay, air, it is inside the bubble and outside the bubble, so bubble. Okay, so here tensile force due to the surface tension is equal to 2 is nothing but what, it is having a two side contact in air, one inside and outside. So that 2 into sigma into circumference, 2 into sigma into circumference is given by phi d, it is equation number 1. Similarly, another force is pressure forces on area phi d square by 4. So again P phi d square by 4. Oh, equation number 2. Equating 1 and 2, will get that P is equal to 8 sigma by d. 8 sigma by d. So in the previous we will get that 4 sigma by d, and this is 8 sigma by d. 8 sigma by d. Surface tensions on the hollow bubble and the surface tensions on liquid droplets. Okay. So we will get that different equations. Okay. So it is it is that is 4 sigma by d, and it is 8 sigma by d. Okay, next one is surface tension on a liquid jet. Surface tension on a liquid jet. Okay, uh, liquid jet of the diameter d and the length l. So you can take one liquid jet which is having the diameter of d and the length is l. From this to this it is having the length l and its diameter is d. Again you can cut it into two phases, and it is subjected to the tensile forces, so that is denoted by the sigma. Okay, so tensile force is given by sigma into 2L. So one L and another this side L. Okay, 2L, that is equation number 1. Again, for pressure force P into area of the semi-jet. So that is given by P into L into D. This is the area of semi-jet, L into D. L into D. That is equation number 2. Again, by equating these two equations, we will get that P is equal to sigma into 2L divided by L into D, or 2 sigma by d. 2 sigma by d, you can get cancelled here, l and l, these two will get that is 2 sigma by d. This is the P is equal to 2 sigma by d for surface tension on a liquid jet, and this is for the surface tension on a hollow bubble, and this is for the surface tension on liquid bubble. Then just we have to take the two forces, tensile forces and pressure force in this case also, and here also tensile forces and pressure force for this hollow bubbles, and for the liquid jet also you can get take the two forces. The one is tensile forces and pressure forces. Equating these two equations we will get the pressure. Okay, that is P is equal to 2 sigma by L, 2 sigma by D. Now next property is the capillarity. Capillarity. Okay, first we should know the definition of the capillarity. What is the definition of capillarity here? So capillarity is defined as the phenomenon of rise or fall of a liquid surfaces in a small tube related to the adjacent level of the liquid when the tube is held vertically in the liquid. So see here the figure, in the one container we are having the liquids here. This is the liquid. If you kept one vertical tube on this liquid, kept one vertical tube on this liquid, so what happens, the liquid is rising through this uh, rising through this tube. That's why here given phenomenon rise or fall. Sometimes there is a fall of liquids through this uh, tube, and sometimes it is rise through this tube when you have to you immerse one vertical tube on the liquid container. Okay, so rise or fall of a liquid surface is in a small tube related to the adjacent level of the liquid when the tube is held vertical in the liquid. You can, if you held vertical here, and this is subjected to the sigma surface tension, and the this will angle between the surfaces, rise or fall surfaces and the vertical, that is indicated by the theta, and this is the height. Okay, the rise of the liquid surface is known as the capillary rise. The rise, if it is rise in the tube, is known as a capillary rise. Fall of the liquid surfaces is known as a capillary depression. If it is fall, then it is the capillary depressions. Okay, so it is expressed in centimeter or mm. The unit of rise and fall of the capillary is expressed in centimeter or millimeter. Okay, it depends on the specific weight, diameter of the tube, surface tension of the liquid. So this property capillarity is depends upon the specific weight, diameter of the tube, surface tension of the liquid. Okay, so it depends upon these three parameters: weight, diameter of the tube, surface tension of the liquid. The liquid rise and fall of the liquid surfaces when one vertical tube is kept in the liquid, that action is called as the capillarity. Okay, so next one is the expression for capillary rise. Okay, there are two phenomena, one is the capillary rise and one is capillary fall. So now we can see some expression for the capillary rise. So d is the diameter of the small tube, h is the height of the liquid in the tube, sigma is the surface tension of the liquid, theta is equal to angle contact between the liquid and the glass tube. Okay, Next, the weight of the liquid of height in h, height h in the tube is equal to area of the tube into h into rho into g. This is given the volume into rho into g. So that is area is 5d square by 4 into h into rho into g. This is the weight of the liquid of height h in the tube. This is the weight of the liquid of height h. So that this is the weight of the liquid in the height of h. Okay, that is given by what? 5d square by 4 into h into rho into g. Next, vertical component of the surface tensile force. Vertical component of surface tensile force is equal to sigma into circumference into cos theta. Circumference into cos theta. So sigma circumference is given by 5d into cos theta. For equilibrium, by equilibrium or equating these two, we will get that 5d square by 4 into h into rho into g is equal to 5 into sigma into 5d into cos theta. So h is equal to, we can simplify it, we will get the 4 sigma cos theta by rho g d. This is the height of the liquid in the tube, height of the liquid in the tube, and the okay. Next, that h is equal to rho 5d by, so that is again 4, this is the height of the liquid. The value of theta between the water and the clean glass surface is approximately equal to 0. That is, the value of theta is equal to 0 when between the water and the clean glass surface is approximately 0. If you put that theta is equal to 0, that's cos 0. Hence, cos theta is equal to unity. That is, cos 0 is equal to 1. Then the rise of water is given by, if it becomes 1, then it h is equal to 4 sigma divided by rho g into d. Rho g into d. This is the height of the liquid in the tube when it is kept inside in the liquid. Okay. So next one is the expression for capillary fall. Expression for capillary fall. So here h is again height of the depression in tube, surface tension acting in downward directions and equal to rho 5d into cos theta. Same. Okay. Force due to the hydrostatic force acting upward and equal to intensity of the force pressure at depth h is depth h area h into area. So here 4 5 5 5 by 5d square by 4 is equal to what? Rho g h into 5d square by 4. These two get cancelled. Equating these two will get the h is equal to 4 5 cos theta by rho g d. Expression for the capillary fall, and this is the expression for the capillary rise. Both are same. Here both are same in the capillary actions. Okay. So next property is the vapor pressure. Next one is vapor pressure. So here temperature of the liquid is 20 degrees Celsius and atmospheric pressure. Okay. Temperature of the liquid is maintaining at 20 degrees Celsius and it is also having the atmospheric pressure. This liquid will boil at 100 degrees Celsius and it gets start vaporization takes place. Vaporization takes place. The molecules escapes from the free surface of the liquid. Okay. Vapor molecules get accumulated in the space between the free surface of the liquid and the top of the vessel. So these accumulated vapor exert a pressure on the liquid surfaces. This pressure is known as the vapor pressure. This pressure is known as the vapor pressure. So here whatever the sentence here he has given, that we have to explain with the help of this figure. So we can take one container. So inside that container we are having some fluid. Half of the container will having the fluid or liquids. So if we add the heat to this, and that liquid is maintained at the 20 degrees Celsius, and the pressure of that liquid is atmospheric pressure. Whatever the container liquid is there, it is having 20 degrees Celsius temperature and the atmospheric pressure. Okay. If you give the heat, if you add up heat to that liquid, so what happens? It starts boiling at 100 degrees Celsius. The whatever the liquid is there, it starts boiling at 100 degrees Celsius and vaporization takes place. The liquid vaporization takes place after 100 degrees Celsius. That vapor droplet will move in the upward directions and get collected or accumulated on the surface of the vessel. This is the vessel or the container. So all the droplets will get accumulated on the surface of the vessel, whatever the he has given here, space between the free surfaces of the liquid and top of the vessel. This accumulated vapor exerts the pressure on the liquid surfaces. So whatever the accumulated droplets are there or vapors are there, these exert pressure on the liquid surfaces. So again these droplets are vapor will exert some pressures on the liquid surfaces. This pressure is known as a vapor pressure. Whatever the vapor droplets will exert the pressure on the liquid surfaces, that pressure is called as a vapor pressure. Vapor pressure. What is the vapor pressure? If you are containing in one vessel, we are containing some liquids. Okay, that liquid is maintained at 20 degrees Celsius and at atmospheric pressure. If you add heat to that vessel, so what happens, it starts boiling after reaching the 100 degrees Celsius and gets vaporization takes place. So that vapor will accumulated on the top surface of the vessels. So after get those vapor droplets will exert some pressure on the liquid surfaces, such that pressure is called as the vapor pressure. That pressure is called as a vapor pressure. Okay, that is the another thermodynamics properties of the liquid vapor pressure. Okay, next one is cavitations. Next one is the cavitation. So here consider a fluid is flowing in a system. Consider fluid is flowing in a system. One you can take one system. Inside that system the fluid is flowing. If the pressure is at any point in this flowing liquids, if the pressure is at any point in this flowing liquid becomes equal or less than the vapor pressure, whatever the pressure is there, that is pressure of the liquid is there that is flowing in the inside the system, that pressure is equal or less than the vapor pressure, the vaporization starts. At that time vaporization starts, the bubble of these vapor are carried by the flowing fluid into a region of high pressure where they get collapsed. Okay, so in one system the fluid is flowing. Okay, the fluid is flowing. Okay, so that pressure of that fluid is less or equal to the vapor pressure. So at that time what happens, the water gets vaporized. So this vaporized bubble will carry along with that flowing fluid, and that they are get collapsed when they reaches the high pressure region. When they reaches the high pressure region, that those vapor bubble will get collapsed, giving rise to the high impact pressure. Again the pressure of the liquid is get increases due to the collapse of that vapor bubbles. Okay, this collapsing bubbles causes the erosion and cavities. So whatever the collapsed bubbles will raises the pressure, that will causes the erosion and cavity. This phenomenon is known as cavitation. This phenomenon is known as cavitation. This is a very important thermodynamics properties of the fluid. Okay, cavitations. Okay, and thank you. With this we will end up the today's classes. Okay, thank you.